So our next speaker is Ilia Ilmer, who is, I believe, a graduate student at City University of New York in computer science, and has done a lot of really nice work on structural identifiability tooling in Julia, and is going to give us an introduction to that. So please take it away, Ilia.
Thank you for the introduction. My name is Ilia. Hi, everybody. I am a PhD candidate at the Graduate Center at the City University of New York. And today I will present a quick tutorial on structural identifiability solution in Julia. My research topic is parameter identifiability algorithms. And in this talk, I'll first introduce the identifiability problem. I will present two Julia-based solutions. One of them, namely StructuralIdentifiability.jl, is included in SciML framework. SciML infrastructure. The other one, a structural identifiability analyzer, is a Julia port from Maple of another identifiability algorithm that's very efficient. So we'll go over the differences during the example section. I will do a quick live coding demo, and then we'll highlight some differences and how one package can complement another during the conclusions section. So what is a structural identifiability problem? And well, in general, parameter identifiability deals with situations where we are given an ODE model and we would like to know whether we can determine parameters of that model. And one way to do it would be to set up an experiment, measure certain variables, certain state values, and then try to manipulate the data to get the value of a parameter. A structural identifiability is a theoretical notion that can answer that question from a symbolic ODE system. Such structural identifiability can be categorized further into global and local. So global identifiability is when a parameter's value can be determined uniquely. And we say a parameter is locally identifiable, or local identifiability case is when there are finitely many solutions for the current parameter. If neither of those situations occurs, and maybe the parameter has infinitely many values, then we say that such parameter is non-identifiable. Now, there are ways to mitigate this issue. I will mention them, but I don't think I'll have enough time to kind of cover in full details. But we'll definitely talk about what can be done for that case. So let's consider a simple example. We have the following input structure, and this structure will be preserved for either Julia package, either SciAN or structural identifiability. So we have an ODE, of which there could be more than one, but for this example, let's consider a single one. So we've got two parameters and one state variable, and we have an output function. Consider this something that can be measured during the experimental stage. And so if we were to plug this into each of the packages, SciAN, Structural Identifiability Analyzer, would tell us that the initial condition and the parameter B are globally identifiable, while parameter A is only locally identifiable. That does make sense. I mean, measure Y at 0 and you get the initial condition. A is seen with a square, so there will be two values that could satisfy an equation for A. So finitely many solutions for A and unique solution for B and X. Structural identifiability, on the other hand, will tell us that B is globally and A is locally identifiable and will not provide any information about the states. So this is the first difference that we encounter between the two packages. Under the hood of SciAN lies a Monte Carlo algorithm which accepts the ODE model and the probability of correctness. So default probability value is always 0.99, and of course users can adjust it. The value will affect the runtime. So the higher probability of correctness, the slower it might become. And the input ODE model is transformed into a polynomial system from which we first extract the local identifiability information. And then from the local identifiability information in further transforms of the polynomials, we can compute Grobner basis and determine global identifiability report. In the StructuralIdentifiability.jl package, we've got a similar input structure. So we provide a model with outputs and the probability of correctness P. However, the process of determining identifiability is a little different, where we compute something called input-output equations. So we only consider equations that contain input functions, output functions, and their derivatives. And then the identifiability report is based on the coefficients from the equations, a field of coefficients. Now, the structural identifiability package can distinguish between single and multi-experiment identifiability, and we'll see where this is beneficial, and both can be can lead to an incorrect answer. So right now, let's move to a coding example. So I did preload a few packages like structural identifiability and modeling toolkit, as well as some other things that we're going to use to visualize what's going on with identifiability. So let's first create a simple ODE. It's based on the example from the slides where there are going to be 3 parameters now and 2 states. So we're going to create the array of equations. And this is, by the way, all coming from Modeling Toolkit. So this is a Modeling Toolkit-based format for the input value. At the end of this representation, I'll also show the structural identifiability kind of native, a slightly different input format. So let's define a Modeling Toolkit ODE system and define the array of measured quantities. So these are the outputs that I talked about in the beginning. So we'll start with analyzing local identifiability first. So if I run the assess local identifiability function and provided the measured quantities, so first it's going to pre-process the ODE system, which means that it's going to convert it to the data type that's accepted by internals of structural identifiability. Okay, so this is done. Let's see the result. So it tells us that A and B are local identifiable. So the output of this is a dictionary from the symbols to the Boolean value. C is not locally identifiable. And if it's not locally identifiable, it means that it's not going to be identifiable at all. And it does make sense. We consider the output, like we measure something that only in the ODE depends on A and B. So no information about C was provided, which is why we would not get any information about it. So let's compute another identifiability result. This time we're going to get a full picture. So local, global, and non-identifiable all together. So again, it starts with pre-processing, and it's going to go through the stage of local identifiability, and it begins the input-output equation computation. And then there's a lot of internal information about what's going on with the Bronskin computation and so on. It's finally done. So it tells you in about roughly 9 seconds, we got the global identifiability result. Let's see. Okay, so as before, let me put the equation up on the screen. So we have A being locally identifiable and B globally identifiable. C is non-identifiable, so that result is preserved. Okay, so let's consider a slightly more complicated example. So this model comes from oscillatory behavior in enzymatic control processes paper. Let's define the states, parameters, and the equations. So there are 4 states, and we're going to use a single output. So we're just going to measure the first state. Okay. We'll define the ODE system. And let's assess the full identifiability, and it's already done in less than a second. If we display result, we see that almost everything is globally identifiable. I believe B, C, and sigma are global identifiable. Beta and delta are local. And alpha and gamma are non-identifiable. Now, I want to focus on these for a couple of minutes just to visualize what this means. So let's give it, let's actually solve the ODE. So let's provide some initial conditions. Let's give it a time span and some parameter values. And let's define the ODE problem that we're going to solve and plot. So the idea is to kind of illustrate what we're going to do is we're going to plot the solution for 2 sets of values. So as you can see, I'm going to alter alpha and gamma, which I remember, they're not identifiable. So we should be able to, well, actually, we shouldn't be able to see anything changed on the picture, on the plot. So let's visualize what's going to happen. And I will, in the meantime, alter the parameters. So for now, it's just going to plot a single solution. And remember that we're plotting the thing that we're measuring. Otherwise, that wouldn't necessarily make sense. Okay, so here's a function. Looks like kind of decreases real fast. Very nice. Let's create a new ODE problem with changed values of parameters. And let's plot that as well. Right. Let's see. Oh, okay. So as you can see, even though I changed the parameter values, the curves are almost identical. I mean, they're probably even exactly identical. So the parameters are unidentifiable, and so we wouldn't be able to tell that from the ODE. Now let's also show another feature of structural identifiability, where we can check a parameter function of parameters for identifiability. In this case, I'm going to ask, well, is alpha plus gamma or alpha plus g identifiable? If I run this, it does the check, and the result is displayed here in the terminal. It tells me that, no, it's actually not identifiable. So the reason why this might be of use to check a function of parameters is because if some parameters may not be identifiable, there may be a function that can be identified. Okay, so now let's consider an example where we use the structural identifiability native kind of input. So I'm going to zoom out just a little bit to show the full ODE. So it does kind of look like what you would expect to be written on paper. I'm going to close the plots here. Right, so if I call this, it's going to define ODE, give you a quick summary of states, parameters, and output functions. And if I call it assess identifiability on that, I see a warning saying that the result that it provides, and let me display the result, might be only valid for a multiple experiment case. Well, the result that it tells me is K1 is globally identifiable, so is K2 and EB. As a quick note, let's check this identifiability for these two functions. And this time, we didn't see any warnings. And locally, these functions are nicely identifiable. So it's another example of where you can identify two functions of parameters. Now let's go ahead and follow the warning. So the warning told us to actually use SciAN to check identifiability of the set model. SciAN is the second package that I mentioned in my slides that also is very well integrated with Modeling Toolkit. One notable difference for now is that we still have to define outputs in the definition of variables, but we are working to make it more compatible with, or kind of more similar to how structural identifiability does it, where you just provide a separate array of equations. So let's define the equation set, create the system, and call the main function of SciAN called identifiability ODE. Okay. All right. So let me actually display the result. Did I not function? Okay. No, I think now it works. Okay. So yeah, it starts with a similar process of pre-processing and converting the input from the Model Toolkit format to the appropriate data type. It does start with the local identifiability report and then proceeds to the global identification report. And as you can see, so before, structural identifiability told us that these three were global identifiable. But that was only valid for when you perform more than one experiment. Turns out that if you perform a single experiment, you only get identifiability local, but not global. So let's try to mitigate this. So I'm going to define this again. And what I will do is I will generate a replica. In fact, I'm going to consider the input to be two ODEs, but with different initial conditions. So if I do that, and okay, so the replicas are generated, I'm going to call my function again. However, I will specify the parameters of the model without initial conditions. Well, because if we did check initial conditions, that would be two separate sets, and maybe it would be not as interesting as some other things that we're going to see. So now, after performing two experiments, so two copies of the input model, we get the same identifiability result as structural identifiability. So that kind of concludes the slide, the live coding section. And to conclude, we saw two available solutions for parameter identifiability in ODE models. There isn't one framework that would solve everything, so these kind of complement one another. Some may be appropriate for more output functions. Some would be faster when there are fewer outputs and more equations, more ODEs. But both can handle quite large systems. We've got a lot of work planned for enhancement of the underlying like Grosvenor basis computations and integration with more SciML frameworks. We also currently have a Maple-based solution on the web that combines these algorithms and some more extensions. And we're also building a Julia web-based solution for the web. That's all I have. Thank you very much to the organizers. And here are some references that I used. Thank you.
Yeah, thank you. Very nice talk. So I think we've got a little time for some questions since you started late. So there were a couple on Discord. So the first one was asking, can you use this in combination with a Turing.jl model that involves ODEs?
Right. I don't think that right now it would be compatible, but it's something certainly we would consider looking into. Yeah, so it's not right now, to be to give a short answer, not right now, but that certainly would be interesting to look into more, how to make them compatible with ODEs that may be coming from Turing.jl.
One of the other Discord questions was asking if you could say a little more about maybe the notion or the differences between global and local structural identifiability.
Yeah, so when let me actually maybe consider this example. So the biggest difference between local and global is that if you were to solve this equation, you would actually, like, maybe even if you don't have the value of b, right? If you have x dot equals a squared times x, if you solve it, you can find the value of parameter a, but because a is squared in the ODE, you will be able to identify a squared uniquely, but not the value of a itself, right? Because whatever a squared might be equal to, maybe actually let me write it down. So if you identify a squared to be something, then a will have plus minus that value, right? Well, to the square root of something. So there are two values. However, a squared is identified uniquely. So that would be global identifiability when there's one solution. And a local identifiable parameter can have more than one, but finitely many solutions. I hope that clarifies the question.
I hope it did. Okay, I think we got one from YouTube. At least I think that's the source. Asking, can you do identifiability of initial conditions?
Yes. So initial conditions are identified by SciAN. So SciAN actually considers the output functions themselves, and the initial conditions will come from here. Structural identifiability doesn't check for initial conditions because the underlying equations that it considers are input-output equations. So they only contain y's, and if I don't have an example with an input function right now, but if there was an input function, well, maybe b is an input function, right? So there wouldn't be any state left, basically, during the process of identifiability computation with structural identifiability. So to answer shortly, SciAN can identify initial conditions. Structural identifiability cannot, and the difference is because of the underlying algorithm.
Okay, actually, we just got another in. So can the parameters be an array, and if so, is identifiability the same for all elements? So I'm not sure. Maybe you know exactly what that's asking.
So if if I understand the question correctly, let's say you would like to define a parameter q that would go from 1 to some number.
That might
currently, this type of symbolic definition is not supported, but we're working on supporting this and resolving the issue. So if that is what you mean by a parameter array, then it's not supported right now, but it will certainly be supported in the future. We'll work on that. Yeah.
Cool. I think I actually had one question myself, which is, I don't know the kind of relevant theory or algorithms in this area, but is there much work and kind of known good methods if you have stochastic problems like SDEs, for example, instead of ODEs, or jump processes, which is what I simulate a lot?
Right. So I don't really work with stochastic differential equations. I don't think I can answer the question. I believe there are works, but I don't think I would be. I don't think I know enough I'm not familiar too well with them to kind of give a solid answer. But that's definitely worth looking into. I believe there is research done, but I just personally don't work with stochastic differential equations.
Okay, great. Well, then I guess we'll stop there. It's about time to start our next talk. And so thank you again for a really nice talk.
Thank you very much.